Hello, everybody, and welcome to the June 2022 edition of the San Francisco Bay Area PostgreSQL Users Group Meetup meeting. Uh, our guest today is Jonathan Katz of Amazon, who is going to talk to us about getting our insecure PostgreSQL passwords to SCRAM. During the presentation, if you have any technical issues, please message the organizers and we will do our best to assist you. If you drop out of the meeting and are unable to rejoin, you can post a message on the event page on Meetup, which we're monitoring during the presentation, and we'll help you troubleshoot and get back in. Before we get going, just a few announcements. The San Francisco Bay Area PostgreSQL Users Group is associated with the United States PostgreSQL Association. We are an official affiliated Postgres users group, and we are pleased to be so. As a disclaimer, I'm the president of PGUS, but we were affiliated before that, so they're two separate things, but important to disclaim. Our other sponsor is PostgreSQL Experts, which provides the video support. Other disclaimer, I work at PGX. And now with that, I would like to turn things over to our speaker, Jonathan. Give me just a moment to make you the presenter.
Thank you.
And now, the floor is yours, Jonathan. Take it away.
Awesome. Thank you, Stacy. Well, again, thank you for having me back, and very happy to be here. So let's talk about one of my favorite topics. Oh, that's the wrong view. There we go. All right. So as Stacy said, my name is Jonathan Katz. I'm a principal product manager at Amazon. And I've been active in the Postgres community for a pretty long time now, to the point where I'm starting to lose track. I'm involved in a lot of the governance aspects of the project, including the core team, the release team, and other fun things. And the topic today actually came about through my own exploration of how authentication works in Postgres, in particular, when I contributed a very small patch around something around SCRAM that ended up opening a code path that led to a CVE and an out-of-cycle release. So after that, I decided I wanted to drill into this more, understand SCRAM better, and actually explain it in a way, because it is a general purpose method. It's not just Postgres. With Postgres 14 coming out, SCRAM is actually taking more prominence because it is the default password method available in Postgres. So before we start, just briefly about my company. I work on the Amazon RDS team, and our goal is to provide a managed database experience that lets you focus on all the things around application development, so we can focus on all the things around production management of databases, failover, backup management, monitoring, etc. In addition to Postgres, we offer a wide variety of both open source and commercial engines they can host on, as well as Amazon Aurora with both a Postgres and MySQL compatible edition. Now let's dive into passwords. So first, we're going to start about, in order to understand SCRAM, it helps to understand, I guess the life cycle of passwords within Postgres, the full history of it. And we are going to dive deeper into the various mechanisms in terms of how SCRAM work, and then, conclude with a demo to show how to upgrade your existing systems to using SCRAM. So where does this all begin? Logging into Postgres. And something that I can say, even I've taken for granted, through the years, is that, when you log into Postgres, things just work. You type in a name, maybe, I fat finger a password, I can't get in, but then I type it in again, and everything just seems to work. But what actually just worked? I don't know, what's going on behind the scenes, because all I see is that I have a password prompt that works. And there were different methods of storing passwords and validating passwords for Postgres version 10. The first being plain text, which we'll talk about briefly, and as well as MD5. Way back, Postgres also supported using the OS level crypt method, but it was deprecated. I don't remember when, but it was a long time ago. Crypt does a two-way encryption, so you can encrypt it and decrypt it, whereas the other methods were one-way encryption. Well, except plain text, which is no encryption. So how did Postgres store plain text passwords? Well, it's just plain text. If your password was password, that's what got stored. And it was also communicated in plain text. There was no hashing, no way to actually, add any obfuscation to the password. This method was actually kept, MD5 was introduced a long time ago, but we kept the password method around for a long time just to ensure that all the drivers implemented the MD5 protocol. support for plaintext passwords were dropped in Postgres 10, but actually the plaintext protocol still exists in Postgres. This is used for a variety of different other authentication methods where we need to pass the credential back to that method to do the validation there remotely. So LDAP is an example of that. And actually, maybe as an aside, that if you're using LDAP, particularly with Active Directory, you should use the GSS API method or the Kerberos method instead, because that's not passing around plaintext credentials. So what was the authentication flow? A user would come to Postgres and say like, hey, I'm a user one, I want to authenticate. Postgres says, great, tell me your password. User says, well, my password is data lake. Sends it over plain text. Postgres now does it, does an equals. Does data lake equal data lake? Yep, you're authenticated. So very simple, but it has some issues. If you're not using any sort of encryption on it, then if someone's eavesdropping to the conversation or scanning all the traffic on your network, they have your credential and they can very easily impersonate. So we can use transport layer security or TLS to mitigate the risk of this. In Postgres, everything's still referred to as SSL, but really it's using TLS at this point. And if you're not familiar with TLS, effectively it performs a secure handshake between two parties and encrypts all the traffic between them. So that way, if someone's eavesdropping, everything's is encrypted across the wire. In Postgres, if you specify host SSL authentication type in the PGHBA file, which is the file that controls how people can connect to Postgres and how they can authenticate, that will force TLS connections. What's also cool is that you can use certificates as part of TLS to authenticate to Postgres using the cert method, which is one of my favorite methods of authentication. And Postgres 12 adds something called client cert equals verify full, where you can combine certificate authentication with another message, such as another authentication method, such as SCRAM. So you basically can get two-factor authentication starting with Postgres 12, which I think is really cool, so long as one of the factors is using certificates. Now, in this example, that if we're using the plain text method and the imposter tries to listen in, they're not going to be able to, because that encryption is that communication is encrypted. But that doesn't mean they can't necessarily get the credential out of Postgres. And here's a common example. You have someone who is like, hey, there's an issue in production. Can you get me a dump of the data so I can debug something? I'm programming some JavaScript. I really want to see the exact source of the data before to try to debug it. It's okay. You can run pg dump all. And if you inspect the pg dump all file, part of this is that you have to recreate the users. And when you look at what's actually going on, you can see like, oh, user one, oh no, why does it keep clicking? So user one has a password at data lake. So it's right there. You have the credential. So the plaintext, even with like TLS communication, there's still ways for someone to acquire the plaintext password. So we can do a little bit better than that. And that's where the MD5 authentication method came in. So the way that you create an MD5 credential in Postgres is that you have a plaintext password, you append the username to it, you take an MD5 hash, and then you prepend the literal string MD5 to it. And that's what's stored inside Postgres. And Postgres performs something called the MD5 protocol. It's a special protocol to Postgres that allows you to communicate and verify the password over it. So that way you're not just sending the exact MD5 hash over the wire, because that's effectively the credential. You add a little bit of obfuscation to it. Now, we know that today the MD5 method is considered weak cryptographically, that there's newer methods to use in order to hash passwords. But we're still going to walk through this to see some of the ideas that came out of it, and also look at some of the weaknesses of using this method, because this is, to the best of my knowledge, still the most widely deployed Postgres password method. So how does the authentication flow work? User says like, hey, I'm user one, I want to authenticate. Postgres says, okay, we're going to use the MD5 method. I'm going to send you 4 random bytes over. So remember that to compute the MD5 hash that's stored on the server, you need the plaintext password and the username, combine them, and prepend MD5. So that's step one. Now, to do the challenge over the wire, you take that hash, and then you you add the 4 random bytes to the end of it, take another MD5 hash of it, and then prepend MD5 to it. And that's what you send back to the server. Now, the server already has your MD5 credentials stored on it, so it can compute that same hash that you have and it's able to determine whether or not you actually know the password. So even if you eavesdrop on it, the eavesdropper will see the 4 random bytes, but over the wire, the eavesdropper only sees this hash, which is not the credential. This is a hash of the credential with some other random bytes to it. So the eavesdropper is unable to get the credential because I mean, they might be able to brute force it, but just from listening to the wire, they're unable to determine what your actual password is. All right, so the eavesdropper can't get it in this way, but what about PG dump all? If you look inside PG dump all, remember we have to recreate the credential of the user. If you look at this is actually the password for the user. When you think about it, the way that Postgres is storing the MD5 password, it's username, password, hashed, and then MD5 prepended to it. But that's actually the credential. If you look back at this step, once you have that MD5 hash and you assign the 4 random bytes to it and take your MD5 hash, you can basically impersonate the user. And that's exactly what the imposter can do here, and then say like, hey, I'm actually user 1 because all I need is that MD5 hash. So this method is a bit, while it protects against some things, it doesn't protect against everything, particularly if you're able to get the MD5 credentials some other way. Now, there's a few other things with it as well, that if you're using a common username and password across all your Postgres servers, that credential works across all those Postgres servers. So that way, if you steal it from one, you're able to log in as that person across all the servers in your fleet. Now, there's some other things that you need to be aware of where you can acquire the user credentials. If you use like the create role command or create user command and put the plain text password in it, if an attacker reads the server logs, an attacker can steal the plain text password. That gets stored there. Safer methods are you can use the \password command in PSQL, which prehashes the password on the client side. And similarly, actually, you can prehash the password on the client side yourself if you want to do it manually. Put it into the password clause of create role, and that will work, and that will correctly store the password. But that still logs the MD5 credentials to the server logs, and as I just stated, that is the credential. That if someone has that MD5 hash, they can log in as you. You can also get these credentials from the PG Auth ID catalog view. That does require privileged access, and certain managed services like RDS prevent users from reading from that table. And one could argue that, well, privileged users are privileged users for a reason. You're granting them trust, but just be aware that if that privileged user is compromised, you might be able to leak these credentials. This is a long way of saying that these password methods need to scram. We can do a little bit better, and that's what the scram method does. So SCRAM is an acronym, like most things in computer science. It's the Salted Challenge Response Authentication Mechanism. And what's really nice about this is that this is a standard. It's in an RFC, and Postgres being an open source database and being all about adopting standards, chose a standard password authentication method to implement. So that way, we're not inventing our own secret sauce, so to speak. We're able to use something that's been rigorously reviewed and tested and used in other implementations. Is you can see that there's a whole series of RFCs that go into the SCRAM RFC, and Postgres specifically is using RFC 7767, which defines the SHA256 method of using SCRAM. The original SCRAM implementation uses SHA-1. Postgres just uses SHA256. The gist of all this is that the SCRAM method allows two parties to verify they both know a secret without exchanging the secret. And I'm going to pause on that point for a second. Like this is a very powerful concept that I can know a secret and you can know a secret, and we can both determine that each other knows the secret without actually exchanging the secret. And that's really powerful, because that way we're not leaking the credential out or creating a way for someone to steal the credential because we send out what the exact password is, be it like a hash MD5 password or a plain text password. We can perform this verification, without ever, exchanging, the sensitive information. Now, there's one thing that we do need to share in the beginning, and that's something called a SCRAM secret. And the SCRAM secret is everything that the server is going to need to be able to validate a client knows the password. So the first thing the client has to do is they need to build the SCRAM secret and transmit it to the server. And there's 5 parts to it. There's a digest, the number of iterations for the password-based hashing algorithm. a random salt, something called a stored key, and a server key. And we're going to dive into each of these in the next few slides. So first thing we store is the digest. And for now, that's just SCRAM SHA256. Postgres is only supporting this hashing method right now. Presumably in the future, we're going to support other hashing methods, but this is what's there for now. The next is the number of iterations to use in the password hashing algorithm, which we're going to see what that is in a few slides. By default, Postgres uses 4096. What's cool about this, though, is that you can actually customize the number. When I was playing around with implementing the SCRAM algorithm, I sent up like 8192 with the iterations, and Postgres respects that. So long as I believe it's an integer, you can put in whatever number you want there. So then there's the salt, a cryptographically secure, randomly generated value. Postgres uses 16 bytes for the salt, and it's ultimately stored in a base64 representation. Again, you can choose a random size for your own salt if you're implementing SCRAM for yourself, or if you're even sending up to Postgres. It doesn't have to be 16 bytes. You can send an arbitrary length string. So again, that's pretty cool right there. That if you want to say have a longer random salt, you can do that. So now we need to build the stored key and the server key. And the first step for that is we actually need to create a cryptographic hash of the password. SCRAM specifies doing something called SCSL prep for doing this. And SCSL prep is a way of normalizing the string, removing certain characters that shouldn't be in there. For the purposes of Postgres, well, let me back up. In the RFC, it specifically talks about using UTF-8 encoded strings. Postgres supports more than just UTF-8. It supports a wide variety of encodings. So what Postgres does is that if it detects as a UTF-8 encoded string, it uses a modified version of the SCSL prep algorithm. If the password is not UTF-8, then the step is skipped, and you don't do any normalization of the plaintext password. So I'll just leave the slide up here real quick to show how this works if you're working on implementing SCRAM on your own. This algorithm is defined in the SCRAM RFC, and as mentioned, it's to normalize the plaintext password into a standard form. So then we have to generate the hash salted password, and this is similar to the PBKDF2 algorithm. Basically, what happens is that you take the salted password and you follow the formula that's defined in the SCRAM RFC, and you iterate it over it for a number of whatever number you specify. So for Postgres, the default is 4096 times. And once you're done with that, you get what is the generated salted password. Now, if you look at the MD5 method, at this point, this is what you would store. This is the salted hash password. This is technically difficult to derive, but where we run into issues is when we get into the verification process, because ultimately we would send this credential over, and then effectively, if someone's able to intercept that, they more or less have your credential. So we need to create two things right now. We need to create something called a stored key and a server key. So the stored key is quite simply the salted hash password, HMAC with a client key, and then SHA256 digested. What does that actually mean? Well, so notice right now what we have something called the salted hash password. So we took our plaintext password, we followed this algorithm, we have a salted hash password. We're then going to take an HMAC, or the hash message authentication code. It's a way of digitally signing your content to verify that this content is what you expect it to be. We're going to literally use a key. So our cryptographic key is the salted hash password, and our message inside the HMAC is the literal string client key, exactly like this. We create that, and we have this thing called the client key. The client keys can be very important during the verification process, so we will come back to this. We then take the client key and take a SHA256 hash of it, and it creates something called the stored key. And that's what's going to be one of the values stored by Postgres. And again, the stored key will be important when we're going through the SCRAM verification process. We then create something called the server key. The server key is much like the client key, but instead of using a client key as the message, you use the literal server key as the message. So we create that. We put it into base64. and we have a SCRAM secret. Now, most folks are not going to actually go through the process of manually generating their own SCRAM secrets. The shortcut is you can use the /password feature in PSQL if password encryption is set to SCRAM SHA256. Some Postgres drivers actually support the ability to do this from within the driver, where it can generate the SCRAM secret on the client side and then send it to Postgres. PsychoPG2, I believe, is one of them. And what they do is that they delegate, quite often they delegate to libpq to do that, or they implement this algorithm on their own. And then all you have to do is, in this case, like alter role, your username and the password, and again, you do want to send up the SCRAM secret in that form, not the plain text password, because that's going to get logged into the server logs. Now, do we care about eavesdropping? In this example, I show the eavesdropper listening in on this. So what is the identifying information we send outside of the username? We send something called a stored key, which is a hash of an HMAC using the computed salted password and client key, and a server key, which is an HMAC using the computed salted password and server key. And yes, I'm reading the slides word for word here, but the thing is, like, we're sending like cryptographic mumbo jumbo. Like, there's not much that they can, when you see the verification process here, just from having this information alone, they don't really, an attacker doesn't really have many options in order to try to get your credential. They could try brute forcing the password, and so long as you select a good password or have a high number of iterations on the PBKDF2 algorithm, it's going to be very challenging to do. The other method is to use an MITM attack during SCRAM authentication to drive the client key, which we'll touch on that later. But again, that has its challenges, and this is why it's still best practice to use TLS when transmitting the SCRAM secret. You should be using TLS in general, particularly if you're in an untrusted network, which I would consider just about every network untrusted. And even the SCRAM RFC says to use TLS, when using SCRAM. But even so, when you send up the SCRAM secret, just make sure you're using TLS. Well, so now we have a credential stored. What about authentication? Like, this is what we came here to see. This magical step of being able to do two-party verification without ever exchanging the secret. Well, beyond, we do exchange the secret at one point. It's the SCRAM secret in order to get it stored in Postgres, but we do need to do that. We do need that first exchange. But from then on, we can verify without ever exchanging the secret. So the goals of SCRAM authentication are twofold. First, each party, the client and the server, needs to verify that each one knows the secret, and do that without ever exchanging the secret. During each SCRAM authentication, to prevent replay attacks, each party is going to send some one-time nonces and some session information to make sure that you can't just intercept all this information and constantly replay it in order to authenticate as a user. So let's see how this works in Postgres. We start off with a typical authentication flow, like, hey, I'm user one, I want to authenticate. The server comes back and says, okay, let's authenticate. Here's my available method, SCRAM SHA256. So it comes back to the client, and the client says, okay, we're going to do SCRAM SHA256. I'm going to generate a nonce, a one-time random series of bytes. So the server gets that message, and the server creates its own nonce and combines it with the client's nonce. It also sends back some information with the client to begin the SCRAM authentication process, which includes the number of iterations for hashing the password, as well as the salt. So basically, the server says, okay, you think you know the password. Well, I'm going to give you the parameters you need to set up to generate the information you need to show that you know the password. It's the number of iterations for the PBKDF2 algorithm and the salt. So we think the password is data lake. And well, in this case, yes, the password is data lake. So with knowing the salt, the iterations, and we knowing that we're using the PBKDF2 method, the client can generate the hash password. And if you have a photographic memory, this matches the hash password that was in the previous slide. But remember, that's just still effectively the credential. All we did is that we took data lake and transformed it into this salted hash password. If we just did a straight up comparison, we're still doing no better than the previous methods we looked at. So we need to do a little bit more work. And this is where we generate something called the client proof. So recall that the client key is the HMAC of the salted hash password over a message of this literal string client key. And recall that the stored key is the SHA256 of the client key. Now, again, if we were just to take remember that we stored the stored key on the server. That's why it's called the stored key. And if we were just to transform the salted hash password, all the way to the stored key, again, we're doing no better than what we did before, because that's that stored key just then becomes the credential. So we have to do a little bit more work, but this is going to start with something called the client signature. So we have enough information on the client side to generate the stored key. The stored key, so just remember, we transform the salted hash password to the client key and then to the stored key. The client signature is going to be an HMAC of a bunch of stuff we call the authentication message. This is some of the information that's passed back and forth between the client and server during during the SCRAM authentication dance. And there's a lot of random bits in this. So you can read the SCRAM RFC or the Postgres implementation to see what goes into that. But using that in our message and using the stored key as our HMAC key, we can generate something called the client signature. Now, knowing that we have the client key and the stored key, we create the client signature. Then we finally create something called a client proof, which is an XOR of a client key and client signature. That's really the magical part. Remember, the client key is effectively as good as a credential. The client signature is this like one-time random blob that we generate, but we XOR it together. We've basically hidden the client key within the client signature. And the client key is good enough to get to the stored key, which is stored on the server. So what we have done here is we created this proof that the server, if we have the correct credential and the server knows our credential, we're going to be able to determine that. So this is the magical step right here. So we send over the client proof to the server, and we send over the nonce that we've been keeping across this session, so we can guard against the replay attack. So the server gets the client signature, and remember, the server knows the stored key, and we use the stored key to create the client signature. That's those authentication headers with the stored key as the signing key. So if we're able to generate the client signature and we XOR it against the client proof, we actually are going to be able to get the client key out of it. That's one of the properties of doing an XOR. So if I'm able to get the client key out, and then I take the SHA256, the client key, and it matches the stored key that I have on the server, then I know the client knows the password. And that's really cool, because we're able to transfer over that information, but we're able to do it in a way that's cryptographically safe. Like, we never exchange the secret. At this point in Postgres, the client is authenticated. But in terms of SCRAM, you're actually not done yet. Like, Postgres can return and say, hey, client's authenticated, but the client needs to also prove that the server knows the password, and it's not just saying that is authenticated. We're going to look into in terms of why that is in a couple of slides. So to do this, the server is going to need to create something called a server signature, where it's going to take that stored server key that we have and use that as a signing key against authentication, that same authentication message, to create something called the server signature. So remember that the server key is effectively the same thing as a client key, but it's using the literal string server key instead. So the server is now going to prove to the client that knows the password. It's going to send the server signature. Now, the server signature, we can derive. So once we have that, we know we can generate the server key, because as long as we have that generated salted password, we can generate the server key. We can then generate the server signature using the server key, because it is just the message. It's just basically taking the authentication message that we have and then doing the HMAC against the server signature. And if the server signature matches what we calculate matches what was sent from the server, then we know that the server knows the password, and we're done. We verified both parties know the secret without ever exchanging the secret. We never exchanged the password. We never exchanged the derivatives of the password. Everything we did was either some sort of cryptographic proof or or it did not contain the identifying password information. So what was transmitted? We'll go through this one more time. There's the client proof, which was the client key XORed with the client signature. So that's that cryptographic package. The server signature was a cryptographic package of the server key plus the authorization headers. We also transmitted one-time nonces from both the client and server, so we can't do replay attacks, and authorization headers that excuse me, are unique to this session. Excuse me, I need a quick drink of water. So in this case, an eavesdropper can only impersonate a user if they have that original SCRAM secret and they're able to intercept the client proof and one-time headers. What do I mean by that? So in the SCRAM secret, remember that we do have the stored key, and the stored key is a way that you can derive the client key from the client signature. But in order to do that, you also need the one-time headers that were passed back and forth during the SCRAM negotiation. So you do need to have an MITM there. If you're able to do that, okay, you can impersonate the user. That's a lot of work, but again, please use TLS when you're communicating with your server. Now, we've protected the client in many ways, but what's interesting about the SCRAM method is now we need to account for a rogue server. And why is that? Remember that Postgres says the user is authenticated once the client has sent over the correct proof that it knows the password. But the client needs to verify the server knows the password, because remember, we never directly sent any credentials. So if a rogue server comes back and says like, hey, I verified your client proof, you're authenticated, a client could in theory just start sending information over and interacting with the server, or taking data away from the server. So the client needs to make sure that the server actually knows the password. And that's why we perform that final step for the client to verify the server signature. And this goes beyond just TLS verification. You could say like, well, I'm using TLS. I know exactly which server I'm connecting to. Well, sure, but if that server has been compromised, it doesn't matter that you're verifying the endpoint of it. You need to verify that the server actually knows the credentials as well. So this leads to the case of an MITM attack. So how do we know that the server instance is the correct one? Well, the Postgres verify full mode, I still say is the best way to do that, because basically you can validate both the server endpoint and identity. You have to verify that your TLS certificate belongs to a trusted certificate authority. But starting with Postgres 11, we introduced channel binding, which is a way to ensure that the TLS handshake that was made between the client and the server extends back up into the application level, and can be used as part of the SCRAM process to maintain the fact that this channel we're still over the same secure channel that we originally thought that we were in. Where this became very useful was in Postgres 13, where a Postgres client could force the channel binding. Up until then, there's the potential for a downgrade attack, where a Postgres client could say like, hey, I want to use channel binding. And a server could say, well, I don't support channel binding, so let's just use SCRAM SHA256. But with Postgres 13, you can basically force channel binding on the client side, and the client can say like, well, if you don't support channel binding, I'm not going to do this. I would say if you want to use channel binding, sure, great, go for it. But SSL mode verify full will still give you the best validation of your server endpoint and identity. Even better, use them both together. Then you get the best of all worlds. So how do you upgrade? This is a very good question. If you're not starting a new application on Postgres 14, then you may need to have some steps to upgrade. So first, ensure your driver supports SCRAM. Actually, if you go to the list of Postgres drivers that the community maintains, all of them support SCRAM now. In your Postgres conf file, you're going to have to make sure password encryption is set to SCRAM SHA256. And again, starting with Postgres 15, this is the default. You can keep MD5 as your authentication method in the pghba.conf file until all the passwords are rehashed. And this is a way to allow for an upgrade mechanism. So that way, if people are still using the MD5 method until everyone's upgraded to SCRAM, it will still work. We're going to see a demo of this in a second. Now, if you want to enforce that everyone's using SCRAM and no one's using MD5, once all the passwords are rehashed, you can go back to the pghba.conf file and switch the authentication method to SCRAM SHA256. So what better way than to see this in action? So first, if it's a little bit hard to see, please chime in. So I'm in my terminal, and I have, let me first log in as a super user. So I have two users that I created. And both have MD5 passwords. So one I called test, and one I called always MD5. Should need to make this a little bit easier too. So always MD5 apparently does not have an MD5 password, but the test user does. So I'm going to first, for purposes of this demo, I'm going to ensure that always MD5 has a proper password, a proper MD5 password. Okay, so both have MD5 passwords. So I'm going to log in as the test user. Actually, first I'm going to prove that I can log in as both users. So here's how I set up my HBA file. So on my localhost connection, so yes, as you can see, I have a bunch of trusts set up, but we're on my local machine. But if I'm going over, my TCP port, I set it up so that MD5 is the method. So, and keep in mind during the transitional period, MD5 can support both MD5 and SCRAM. All right, so let's log in. First, we're going to do my test user. So I'm prompted for a password. That works. And now we're going to do the always MD5 user. You see, okay, so nothing up my sleeve. I can log in as both. Both of these just use the MD5 method. So let's go into the test user. So we'll make sure we have the password encryption set to SCRAM SHA256. Great. So I can now change my password. All right, so my password should be changed now. And just to prove it, I'm going to log back in as my privileged user. We see now the test user has a SCRAM password. All right, can we log in as our test user? We can, great. So, and we actually just use the SCRAM method right there. And we should still be able to log in as our always MD5 user. Cool, so we were able to upgrade the password. Now, let's say, we just want to force everyone over SCRAM. We're tired of having the MD5 method available. What can we do? Well, that's postgres.com. Well, first we go into the correct configuration file. And we change MD5 to SCRAM. We reload our server. So can we still log in as the test user? Yes, we can. And we logged in over SCRAM. But can we log in as the always MD5 user? Nope, because that password hash is still in the MD5 hash. It's not a SCRAM password. So now we've effectively blocked out that user. But what you could ultimately do is you can just rehash the password and then the user can log back in. All right, let's bring it on home. Now, as I said, like the reason I actually originally started researching SCRAM and wrote this talk, outside of writing some code that ultimately led to a CVE disclosure and out-of-cycle release, was because I was really curious. Like I started questioning, like, why does password authentication just work? And questioning it just works can lead to better solutions. And this is ultimately why the Postgres project adopted SCRAM. SCRAM is a general purpose authentication solution that you can use it in your own applications or wherever you need to have two parties verify secrets. There's actually a SCRAM RFC out there specifically for HTTP. I'm blocking on the number right now, but I think it's proposed so over a web request, you don't need to have as many back and forths. You can also there's a few implementations of the Postgres or SCRAM, well, not just SCRAM but Postgres SCRAM. You can see them in the various connection drivers. Actually, I also wrote an example way to create Postgres passwords. So if you need a way to be able to generate the SCRAM secret without and you have access to libpq or /password, it can help serve as a reference. As mentioned, Postgres 14 made SCRAM the default password method. So you should, if you're talking to Postgres 12, Postgres 14, you should upgrade to that. And in general, if you're on Postgres 10 or above, you should make a plan to upgrade your passwords. Like the SCRAM method is much better overall. The verification process is much more secure than the MD5 process. And if your credentials get leaked, it does lessen the blast radius. Even if you're using the same password across all your Postgres instances for the same username, which you shouldn't, but unless you're using a proper SSO system. But if you are, all the SCRAM hashes will look different so long as the salts are unique or you're using a different number of iterations. But in general, you should make a plan to upgrade your passwords to use SCRAM. And that's all. Thank you for attending, and I'm happy to answer questions now.
Fabulous. Thank you so much, Jonathan. I could even follow that. So nice explanation. Good and clear. So now we open up to questions. So if you have a question, you can either use the raise hand function or you can type it into chat. And here we go. Let's see. Okay. Jim Saltzman, you have a question.
Yes. Can you hear me?
Yes.
Maybe?
Yep.
Oh, good. So you mentioned using TLS, but I noticed you just had host on your configuration file. Is that because it tries to use TLS if TLS is available and then fails back to non-TLS connections? Do you know the configuration file?
Yeah, that's correct. So that's what host does. It tries to use TLS and then it falls back to non-TLS. This is on my local machine, and I was only opening it over my local host. So the risk of MITM attack is very limited. But if this were a proper production example, I would have had host SSL on.
And that would prevent the failover to non-encrypted TCP connections and
Correct.
force the TSL. I wonder if there's any reason not to do that, since all the clients these days support TSL. Although I remember there's one reason I didn't want to have a certificate check. But maybe you could talk just a little bit about why you might want to enforce that, and in what situation it would be unlikely to have a client connecting without TLS, maybe.
Okay. So if I can rephrase the question, why would someone not want to connect over TLS?
Right. So I'm sorry, my apologies. What I'm getting at is that there's a lot of different options for enforcing TLS and other various options on top of TLS, including certificate check to the host name. And I can remember a situation in which I wanted to specifically exclude the host name check. And I know this is part of making sure that people have TLS running, but I'm wondering if there's ever a situation in which, when TLS is available, some weird network situation or perhaps an attacker could force the connection to not be TLS.
Okay, so I guess there's two places we can start with this. In terms of, let's start with TLS enforcement. There are two areas where this can happen with Postgres, on the server side and the client side. And let's just look at enforcing TLS. We'll skip verification at this point. So as you mentioned in the pghba.conf file, you can force something. You can basically specify host SSL, and in this case, for any connection coming in, over a TCP, Postgres will say it must be over TLS, otherwise I'm not going to let the person authenticate. But that's the server enforcing it. The client can also do enforcement as well. And in fact, the client enforcement is arguably the more powerful part of this step. The client has a few options in terms of how it can enforce that a server has TLS. There's actually, at one end of the spectrum, there's disable, where basically the client says, I don't want TLS at all. I only want to connect if the server does not have TLS. There are some special cases where that can happen. For instance, you might be in an environment where the Postgres server does not support TLS, or it has to do with the next level up, which is the SSL mode prefer, where the client will first try to connect over TLS, and if it's unavailable, it will then fall back to a non-TLS connection. I actually had to deal with an application that did not understand the Postgres prefer SSL mode. So we tried to connect over TLS to a server that didn't support TLS, but it would not retry to do the connection, over the non-TLS mode. So we had to explicitly do SSL mode disable, and then fix a bunch of software so we could use TLS. So after prefer mode, there's TLS mode require, and that basically means a client is requiring the server to have TLS. It's not doing any checks on the host name, or if it's part of a trusted certificate authority. All it is doing is that it's just checking that it's just basically enforcing that the connection must be over TLS, and if not, then it's going to drop it. Then there's a SSL mode verify CA verify full. In most cases, you want verify full. Verify full basically checks that when you're connecting over TLS, the certificate that the server presents is signed by a certificate authority that you trust. And you provide the certificate authorities as part of the client. You can specify like a certificate bundle that the client is choosing to trust. It then does a check on the host name, or if you're using PSQL, the part that's in the -H, it will check to see that host name is in the certificate being presented by the server. If all that matches up, then it'll let the connection go through. If you're unable to verify the host names, but you want to make sure that the server is part of the trusted certificate authority that you're presenting, you can use SSL mode verify CA. It's not, it's a better guarantee than just requiring a connection. Basically, you're saying like someone else in my certificate space trusts the server, but you're not verifying its identity. Now, are there cases where you might need to choose one or the other? Yes, I think Jim was trying to get at some of those examples. I had a case where I had to use verify CA over verify full because with the server group I was connecting to, you did not necessarily, the host names on the servers would keep changing. That we didn't have a mechanism in place to continue to verify the host names. We did a software update, I'd say 6 months later, that allowed us to enforce verify full on all of them, because verify full is giving you the strongest guarantee that you're connecting to the server that you believe you're connecting to. Jim, does that help answer your question?
Yes, exactly. That is exactly what I was getting at. That was, I don't remember exactly why, but the host name could not be verified in advance. The certificate that it was going to have wasn't necessarily the host name that the clients would be using to connect to it. So I appreciate you clarifying that, because it was a long time ago, and I'm not primarily a Postgres admin, so it's just great to know that this is not something that was bad. Thank you.
Yeah.
Great. Wonderful question. Great discussion. I'm sorry, Jonathan. Go ahead.
I was going to say the TLS, I'd say that's a proper term. The people who are really into TLS, they're going to say you always use verify full. But in the real world, sometimes you have to make some sacrifices.
Great. Okay, and let's see. Next question. Go to chat and see who is waiting.
Can you guys hear me?
Okay.
Hello.
Hi, Gurjit. Yes, go ahead.
Yep. Yeah. I prompted or kind of pinged so many times. Can you hear me? Can you hear me? That I had forgotten my question now. Oh, yes. Now I remember. So you showed, Jonathan, that how to switch over from an older authentication method to SCRAM. And then there is kind of a cutover between the time when the client was using the SCRAM, like non-SCRAM method or MD5 specifically, to a SCRAM method. So whenever that happens, there is a potential for an outage, right? That means like you change the password on one client, but if that same client is connecting from different web servers, different terminals, etc., all those terminals also need to kind of upgrade their mechanism of like from MD5 to SCRAM. Is there a way around that, like preventing that outage?
So there is a coordination problem that when you're rehashing, well, maybe I'll back up a second. I think it depends on how the clients are managing their password. So there's the server side where you have the credentials centrally stored, and then there's the client side. And the client side, depending on how you're storing it, if you're using encryption, a password encryption service, or you're storing it locally in a config file, it depends what you're doing. If you're rotating the password at the same time, so let's say your password's data lake and you're changing it to data lake 123, there may be more potential for the outage because you'd have to rotate those passwords on all the different app services. The other risk area is based upon what Postgres connection driver you're using, ensuring that they all support SCRAM. Because if you're suddenly enforcing SCRAM, or even if you've rehashed the password to SCRAM, but the client's drivers are not supporting SCRAM, you're potentially causing them to fail. So I would say you first have to look at those two areas. The other question I commonly get is how, I'm managing a fleet of, say, like 50 servers, and I have, 100 users going to them. How do I update all their passwords? And, that gets a little bit trickier. And, in that case, you might want to have a middleware in place where, the user authenticates to your middleware, and you use that to translate to, the SCRAM method to have the passwords rehashed. And when all the rehashing is done, you can remove the middleware. That, again, that has its pluses and minuses. Like you might need to maintain the middleware for a long time, particularly if it's, maintaining an MD5 hash, within that. So is there a risk for an outage? Again, it depends on it depends on a lot of different factors. It depends what you're doing. It depends how you're storing the credentials for your applications. I would say, I would start from there and, evaluate how you can do the upgrade method, because there's enough on the Postgres side that will mitigate the risk of an outage. In fact, you can just keep like the MD5 method for as long as you want. If passwords are upgraded to SCRAM, they're still going to use the SCRAM protocol, even if MD5 is set in the HBA file. But if you want to enforce SCRAM and make sure everyone's using SCRAM, then you have to change the authentication method.
Oh, so what I got from that is that there is a transition period the clients can adopt where the server does not enforce SCRAM, but it allows SCRAM as well as MD5 at the same time. Correct. But when the client changes, one user's password has changed from MD5, the storage mechanism from MD5 to SCRAM, the stored password. If the same user connects from another machine, let's say a connection drops, to begin with, I want to clarify that any established connections, they will not be affected. They will be required to provide SCRAM only if they try to reconnect. So established connections are kind of not prone to this problem, but only the new connections will be kind of prone. So you're saying that when we transition the password from MD5 to SCRAM, then we break the connections in a staggered manner and then reestablish connections on the new machines, and then all of the connections will be upgraded. Is that like a viable strategy?
Yeah, that's correct. And as you said, like if you rehash your password to use SCRAM and clients are currently connected, or clients under that user are currently connected, they're still, that connection's going to stay the same. It's only when they try to reconnect will you have to use SCRAM. And it might also be transparent, like based upon the driver you're using, like the reconnect, it might just do SCRAM, without you realizing it. Like in the demo I did, using PostgreSQL, like I switched to using from MD5 to SCRAM, and like, you wouldn't have known.
Right. So I guess what I'm looking for is just like there is a prefer mode in SSL, wherein the client tries the SSL, and if the server rejects, then it tries the non-SSL method. I guess that's what I'm looking for in SCRAM to MD5, wherein the client tries SCRAM. If it fails, then it tries MD5. Like that transition period, I think, is what I'm looking for. I think,
yes.
Yeah. So with that staggered reconnections, that might help.
Yeah, but that's going to be dictated by the server because the server is going to advertise the authentication method that the client is allowed to use based upon what's matched in the HBA file.
Got it. Thank you.
Great. Oh, and Jim had a comment in the chat. I remember what it was now. Our host didn't have host names in DNS, just IP addresses, which is why we had to disable host name verification. And I think certificate verification too, if I remember right. SCRAM is certainly a nice way to defend against the potential MITM attack disabling certificate verification allows.
I agree. In fact, I actually think IP verification might have been added for Postgres 15. I'm going to look that up real quick. I could be wrong. Yeah, allow IP addresses matching against the server certificate's subject alternative name or SAN. So yeah, you should be able to use verify full on an IP address for Postgres 15 coming soon.
That's terrific. Hooray. Cool. Okay, let's see. Let me just check. I don't see any other hands up. Okay. Well, that was a terrific presentation, Jonathan. Thank you so much, and for taking all the questions afterward. I'd like to thank everybody for coming. And just a few things before we wrap up here. Again, thank you, Jonathan. That was terrific, and it's always a pleasure to have you here.
Thank you.
I would, it's wonderful. Can't see you in person, but this is really close. We're getting lots of thank yous and thumbs up and heart comments on the side, so that's terrific. Thank you all. Again, I would like to thank the United States PostgreSQL Association and PGX for sponsoring this particular meetup. Our next meetup will be Wednesday, July 13, Anticipation. What's new in Postgres 15 with Christoph Pettis. Our August meetup is August 10. We will be celebrating World Elephant Day with Elephants at the Watering Hole, a general discussion of all things PostgreSQL, which will also be a joint event with our colleagues at the Portland Pug. So some things to look forward to. Excuse me, some things to look forward to. Also, PGS presents PGConf NYC, September 22nd and 23rd. The CFP has closed. The schedule will be announced in the next few weeks. Early bird tickets and corporate sponsorships are available. As for today's presentation, we will edit the video. We will send a link by the email when the video is ready and live on YouTube. Also, watch our social media channels for that announcement. Speaking of social media, you can find us on Twitter at Bay Area Postgres. As always, we're looking for speakers. We have the next couple months lined up, but come September, we're going to need somebody. So if you have something to share about Postgres, drop us a note. Let us know. We would love to have you. And again, thank you, Jonathan. Thank you, everybody, for coming, and we'll see you again in July. Bye.